Welcome back. So last time we learned a lot about angular momentum by solving the angular equation for problems where my Hamiltonian is spherically symmetric. Today we're going to finish up talking about spherically symmetric Hamiltonians, but we're going to do it by studying the radial equation, which, as we alluded to in the last video, is the one that we've really been waiting for because it's the one that tells me information about the eigenvalues of the energy. So just to quickly remind us, in 3 dimensions, my Hamiltonian is it's got the momentum part, the p squared over 2m, and it's got the potential. And again, the r here is the coordinate that is the radial coordinate, so distance away from the center of the problem. If I write that down in the position basis, right, I get that the momentum operator has that gradient in it, and so I end up with the Laplacian of the wave function plus the potential times the wave function. And of course, this is just the 3-dimensional version of the thing that we've been working with for weeks. So I'm going to assume that we've already solved the angular equation. Why? Because we just solved the angular equation. But when I solved the angular equation, I came up with those spherical harmonics as my solutions. And those spherical harmonics used the boundary conditions of the problem to give us 2 quantum numbers, right? It gave us L, which is the quantum number associated with the angular momentum, the total angular momentum, and it gave us M, which was the quantum number associated with the Z component of the angular momentum. Okay? But I'm going to assume that by doing that, I came up with those 2 quantum numbers because I'm going to need L in order to solve the radial equation, right? That's something that I actually have to plug in there. And if I do that, that LL plus 1, which is the eigenvalue of the total Hamiltonian operator, shows up in my radial equation, and I get this red equation for R, right? And that's the eigenvalue problem that's actually going to give me what the eigenvalues of the energy are. And looking at it, it doesn't look fun, right? And I'm writing it sort of in its most compact way. You can use the the product rule on that first term to get 2 derivatives, right? One of them will look sort of normal, one of them won't. To go any further, of course, though, I actually now have to specify what the potential is, and that's kind of interesting that we could do the entire angular part without actually knowing what the potential was. Of course, that's because our symmetry meant that our potential didn't contribute to the angular part at all. But now, in order to solve this equation to actually get some energies out, I need to tell it what problem we're solving. And so now we're going to do the big problem, right? The hydrogen atom. And I'm going to put that in quotes because really we're doing hydrogen-like atoms because I'm allowing for there to be sort of an arbitrary charge at the center. So Z is the atomic number, it tells me how many protons there are, right? That's the thing that's generating this potential. And we all know what the expression for the electric potential is due to a point charge, right? It's 1 over 4 pi epsilon naught, 1 over r. And I hope I didn't make that mistake in more places than this. Of course, it's just 1 over r. I know I did on the next slide, right? Potential is 1 over r, force is 1 over r squared. Anyway, at least we caught it. All right, so I'm going to be solving for all problems where I have something like an electron, which is, that's the second, I have an electron, right? Which is influenced by the central potential due to a number of protons located at the origin. And that's what we're going to call the hydrogen atom, even though it's really a whole class of hydrogen-like atoms. There are a lot of people here who really care about atoms that look like this, right? Where you have some effective charge at the center. Maybe you have extra electrons that you're not going to worry about, but you basically have 1 electron in some outer shell that. Anyway, I'll let Aaron tell you about that next semester. Okay, here's my mistake again. So let me just erase that squared before anybody sees it. Right now, this is a differential equation, right? And it's one that can be solved. Your book solves it. Every, podcast solves it. YouTube solves it a bunch of different ways. What you do is you take R and you break it up into an asymptotic form, just like we did for the harmonic oscillator, right? And you then do series, and it's a thing. I'm not going to do it here, okay? Because those algebraic steps are going to, they give us what the wave functions look like, but they don't contain that much information about the physics of what's going on in that wave function any more than us just talking about what's going to happen when we solve that wave function the way that we solve it. Okay, And basically what we're going to do is we're going to come up with all of these different, all of these different solutions. We're going to assume an asymptotic form, and that's going to give us solutions to this problem that obey the particular boundary conditions that I have. And the boundary conditions here are going to be that the wave function has to vanish at infinity, right? And that its derivative has to vanish at infinity. And those boundary conditions are enough to tell me that the radial wave function is now going to introduce a new quantum number, right? That is, those boundary conditions are going to quantize the radial wave functions. And it's going to give me this... I have to... there's no 2 there. Okay. It's going to give me... it's going to give me the radial wave functions, right? And those radial wave functions now are going to have two quantum numbers associated with them. The L, which I got from the angular wave function, right? And that's something that I put into this part. And N, which is going to be the new quantum number that's generated by my boundary conditions at infinity. And N now is what we're going to eventually call the principal quantum number. And that's the quantum number that I get by solving the radial equation. Okay, N is gonna tell me something about the eigenvalues of the radial equation, right? N is going to be the new piece of information that I get by solving this equation specifically. And so if I wanted to look at what those solutions look like, and now I think you'll understand looking at this page why I chose not to do this out in this video, I can write down what the full solution is, right? Then this is just the radial part of it, right? The R sub NL, which is the radial solution that corresponds to quantum numbers N and L, are given by this big old thing, right? Which has a normalization factor, and it has the associated Laguerre polynomials, and it has e to the, it's got all of our favorite things in it, right? But it is a solution to this differential equation, right? And therefore, it's the solution to the differential equation, or it's the family of solutions. But also what I know is that when and by the way, there's this special combination of factors, 4 pi epsilon naught h bar squared over e squared m. That is the Bohr radius, okay? And that's the thing that's the number that really sets the scale on a lot of these other numbers that I've been working with here, right? And that's something that you might remember from your modern physics class. Anyway, but these solutions now are the wave functions, right? They tell me something about the distribution of probability density of where an electron's going around an atom might be. And in your problem set, you're going to draw some beautiful graphs associated with the solutions here. But it's not that important from sort of from a spectroscopic perspective, right? It's not that informative if I'm just trying to look at say changes of energy states of these atoms. For that, all I really need to know are the quantum numbers, because the N now, the N is going to be that additional piece of information. And so my radial solutions, again, they depend on the angular quantum number, right? They depend on that total angular momentum. And that's because if my electron has a different amount of angular momentum, then that's going to affect how I measure its energy. But now this N, this radial quantum number, is the piece of information I get from solving the radial wave function and imposing those boundary conditions. And it's important to note that I think other than the existence of N, which is by far the most important part, the most interesting part of solving this problem, when I do the differential equations, I also come up with the fact that this principal quantum number, the radial quantum number N, has to actually be bigger than L. Okay, and now we can talk about all sorts of reasons why that has to be, right? But the N, which corresponds to the energy, has to, in whatever units we're using here, be bigger than the angular quantum number. And I'm actually going to turn that statement around later. But here, because L goes into the solution and N comes out, we do want to establish the fact that when I'm solving this problem, I find out that I can't just get any N. N has to be bigger It has to be bigger than L. And I can use all of that to reconstruct the wave function, right? I take my RNL and multiply it by my YLM, and I can get the entire three-dimensional wave function. But the N also gives me the eigenvalues of the Hamiltonian, right? N, this was our big goal the entire time, right? To get what are the allowed energies of this system. And what I find when I do this analysis, when we plug in this differential equation, is that the energies are all proportional to this thing called the Rydberg, this combination of constants that is equal to 13.6 electron volts. And I should be a little bit careful with the Rydberg is 13.6. It's also proportional to the number of protons squared, although I guess for hydrogen we often said Z to be 1. But then the energy states go as 1 over n squared, right? So n equals 1 is the lowest energy state because it's minus 1 over 1, which is minus 1 times 13 points. That's the binding energy of the hydrogen atom. As I go to higher ends, I go from, 1 over 1 to 1 over 2 squared, which is 1 over 4, right? So that actually raises the energy by quite a bit, right? It raises the energy by 3/4 of a Rydberg. And then as I go up from there, the energies asymptotically approach 0. Now, in principle, right, how many energy levels are there? Well, I guess there are an infinite number of bound states here. And it's interesting to think about how I get an infinite number of bound states from this potential. But again, that's something we'll talk about on your problem set. Okay, so the principal quantum number, n, this number that I get out from doing the differential equations to solve the radial equation, gives me what the energies of the system are. N corresponds to, it determines, it measures what the energy states of this system are, right? And that, again, comes from solving that differential equation and implying the correct boundary conditions. So if I have then the idea or the concept that all of the information of my system is now contained in M, L, and N, after all, those are the numbers that I get from imposing all of my boundary conditions, I can take that wave function, which is, depends on N, L, and M, and I can try to now just talk about the state. Now I can use the ket, right, is equal to, and then I'm going to integrate the wave function over all space so that I can write the wave functions in the position basis. But I can now talk about the state NLM as being the real physical quantity that I get from doing this problem, right? The wave functions are interesting, but they don't help me measure energy differences, right? They don't really help me do a lot of the physics that we're most interested in. What we're most interested in is measuring things like energy and angular momentum and the z component of the angular momentum. And for those, all I need is this idea of a state, because from that state, I can get out all of the measurable quantities, right? That all my three big operators, H, L squared, and LZ, when I act them on that state NLM, will give me out the eigenvalues that I'm most interested in, right? So those are the three quantum numbers that come from the three dimensions, right? The principal, the angular momentum quantum number, and then we call M the magnetic quantum number. It's the Aaron will tell you all about that. But these are the three pieces of information I get from solving this problem. And then, of course, I also get these rules, right? And we talked in the last video about the fact that L has to be an integer, right? It can be a non-negative integer. It can be 0, 1, 2, 3, all the way up. And that M is a positive or negative integer in between minus L and L. The total angular momentum determines what the possible z components of that angular momentum are. But we also learned from doing this that n has to be greater than L, or in other words, L has to be less than n, right? And since n has to be greater than 0, and these are strictly greater than and less than symbols in these first two lines here, since n can't be 0, it has to be 1, right? And since L is strictly less than n, if n is equal to 1, right, which is the lowest state, the ground state, then L has to be 0. And if L has to be 0, then M has to be 0, right? And now you can see how I develop all of these rules about, well, if n is 1, then if n is 2, then L can be 0 or 1. And if L is 0, then M is 0. But if L is 1, then M is minus 1, 0, or 1. You can see how I quickly generate a lot of states as I go to these higher energy states. Okay. And again, though, it's the boundary conditions that gave us these rules, right? It was solving the differential equation and imposing the boundary conditions that told us what got quantized, right? And these numbers, these quantum numbers, help us to parameterize that problem. And a quick note for the chemists out there, right? So you've seen these before, right? We saw the principal quantum number in modern physics all the time, right? When we were talking about the transitions between energy states of the hydrogen atom. Well, if you took a chemistry class, you would also recognize this notation, because in chemistry we call L the orbital quantum number, right? And instead of calling it L equals 0, L equals 1, L equals 2, we give them these names SPDF, and I think I got them right. I did them from memory, right? Where if I'm in the L equals whatever state, I can look up the letter associated with that. So if you remember in chemistry, if you had like a 2p orbital, right, that means n is equal to 2, p, which is L, is equal to 1, and there you get you can translate between our quantum mechanics lingo and your chemistry lingo pretty straightforwardly. Anyway, okay, here's the take-home messages. The radial equation is hard to solve, but not impossible to solve. Luckily, people have solved it, and there is a solution, and those solutions depend on L, and they depend on the new quantum number that I get by solving that system, which we call n. And n then tells us what the there's a squared missing. The n tells us what the energy eigenvalues are of my equation. And then, of course, I have these rules that n has to be strictly greater than 0, L has to be strictly less than n, and that M is in between minus L and L. And that is the hydrogen atom.